All right, I guess we'll get started. So at the end of last lecture, we were talking about static features in a class. And we had this little utility class here. Now remember, a utility class is just a class where everything is static. So it's got one public static final constant up here. Right? It's got one public static method here. You could, of course, add more static methods and more static fields if you wanted to. Right? But we don't have those in this class. Notice also that in a utility class, because the class is not intended to create objects, you include a private constructor that does nothing. And so this is to prevent anybody from actually trying to make an object of your utility class type. Right? So remember that if you don't have a constructor in your class, the compiler inserts one for you, right? And then someone can make a relativity object in this case. Right? So to prevent the compiler from creating a constructor for us, you include one. It doesn't matter what constructor you include, as long as there's one. You make it private so no one can call it, and that prevents people from making an object of your utility class type. Right? So if you were to actually look at any of the utility classes in the Java standard library, you would find a private constructor in all of those classes. Okay. So that's about it for static classes. Sorry, for utility classes. The utility class is very simple. It's the simplest type of class you can have in Java. Right? All it's got is a bunch of static features. It's also relatively uncommon. Now, what's more common are these things called static factory methods. So you can put static features into a regular class. Right? There's nothing stopping you from doing that. And often you want to do something like what I'm about to show you. Okay, so this is arguably the most common use of a static method, arguably. Right? So a common use of these static methods in a non-utility class, so in a regular Java class, you're going to use them to create what are called static factory methods. Right? So it's static, so you know the method's static. It's called a factory method because it makes an object. Right? Okay, so the reason you want to do this is because you can create a method, so a static method, that behaves like a constructor. Right? So remember, a constructor is supposed to initialize the state of a newly created object. A static factory method makes a newly created object and can initialize the state by calling the constructor in the appropriate way. Right? So they're like a constructor in that they end up creating and returning a reference to a new instance. Right? So you make a new object, and it returns the new object back to the caller. Now, the big difference between a static factory method and a constructor is, unlike a constructor, the method has a name. Right? And that lets you put as many of these things as you want into your class. Right? So remember our point class, right? So it's a two-dimensional point. We have 3 constructors in the class so far. One of the constructors takes in 2 doubles, right? It takes in the coordinate of the point. Now, if you take in calculus, you've probably seen something called the polar representation of a point. Right? So the polar representation of a point, that point right there, right? You specify that as the distance from the origin, so that's r, right? And the angle relative to the x-axis, right? And you do this sort of thing when you're working with circular shapes, basically, right? Any shape that's got rotational symmetry, you often use polar coordinates to represent points on the shape, right? Now, the coordinate of that point, that's just a point on a circle of radius r, right? So the point's just r cos theta and r sine theta, right? No big deal. Now, the problem is, if you wanted to insert a constructor into the point2 class, right, that lets you create a polar point, you have a problem, right? First constructor is our existing constructor, right? It's the one that takes in the coordinates of the point, right? I now want a second constructor, right, that lets you create the polar form of the point. However, right, its parameters are double and double, right? The distance from the origin and the angle relative to the x-axis. Right? And now you've got a problem because you've got 2 constructors with the same parameter lists. Right? Remember, the names don't matter in the parameter list as far as the constructor's signature is concerned. Right? So you've got two constructors that take in two double arguments, and you're not allowed to have that in one class. Right? So that's an illegal constructor overload. Right? Now, if you're designing the class for people to use, and you're expecting people to want to represent points in the polar form, you've got a problem now. Right? Because you really want to give them a constructor that can make a point like that. But you can't put it into the class because your other constructor signature is the same. OK, so what do you do? Right? So you make a static method. Right? So you replace the second constructor with a factory method. Right? So a static factory method, it's just a static method. Right? It returns a new object. You'll also see this called the named constructor idiom. Right? So looks like a constructor, right? But it has a different name. So that's why it's called the named constructor idiom. Right? Because a static factory method can have a descriptive name, and it behaves like using, and it uses, and essentially internally it uses new to invoke a constructor. Right? So it's actually very easy to do. Right? Public static. So you put in a static method, right? Returns an object of the type that you want. Right? So this is we want to return a point2 object. You give it a name. Right? So give it a name that doesn't conflict with anything else in the class. So I'm just going to call it polar. And now you can give it whatever parameters you want. Right? So now I can insert this method into the class, and the signature polar double double does not conflict with anything else in the class. Right? Now how do you implement the method? Well, you just make a point and return it back to the caller. Right? So my point, the x coordinate is just r times theta. Right? The y coordinate is just r times the sine of theta. Sorry. The x coordinate is r times the cos of theta. The y coordinate is r times the sine of theta. Right? And then you just make a new point and return that back to the caller. Right? So it's actually very easy to do. Right? It's very simple. Now, internally, it calls a constructor. Right? So that's why it behaves like a constructor. Right? It makes a new object, returns that object back to the caller. Right? Now, if you look inside the implementation of point2 and vector2, you'll see that there are many static factory methods in the class. Right? So for each of the following non-static methods, so there's an add, subtract, multiply, divide, and negate. Right? There's a matching static factory method. Do I tell you why? Oh, I do. OK. So there's a matching static factory method for each one of these methods. Right? So remember, we have an add method that looks something like, you can call it like p.add. Right? So for add, you can do p.add q, right? Where p and q are 2.2 objects. Right? And that ends up being equal to p equals p plus q. Right? So that's what that version of add does. So that's the non-static version of add. Right? P, Q, Q, V, whatever. I'll change that to V. It's actually you add a vector to it. You don't add another point. Right? So you got P, add V. Now, what do the static versions do? So the static versions, they're all factory methods, so they return new points. Right? So the static version of add creates a new point without changing the point p, right? Or the vector v in this case. Right? So the static version you would call like point2. OK, so now you have a q. So I'm going to make a new point. Right? And I'm going to call the static factory method P and V. Right? And that produces a point like that. Right? So you've got one version of a method, the non-static version, that changes the point that you call the method with. And then you have the static version of the method that doesn't change the point. Right? So it lets you express two different mathematical concepts. And all of the other methods are the same. Right? So subtract, multiply, divide, and negate. Right? There's a matching static factory method that gives you back a new point equal to subtracting 2 points, multiplying a point by a scalar, dividing a point by a scalar, and negating a point. Right? And if you look in the Java standard library classes, there's lots and lots and lots of methods, examples of methods, of static factory methods. Right? So in the integer class, there's a factory method called value of. Right? If you give it an int I, it gives you back the integer object corresponding to I. Right? Copy of we've seen, so that's in the arrays class. Right? Copy of will make a copy of that array and return the new array back to the caller. Format will return a formatted string given that format string definition and a bunch of objects that you want to put into the string, right? Or that you want to get the string representation of. Oop. Right? So that's it for static features in the class, right? There's not really much, there's nothing really interesting conceptual, well, academically, I suppose, right? The important thing to remember is that a static field belongs to the class, right? It doesn't belong to any individual object, right? So all the objects of the class share the same static field. A static method is the same thing. It belongs to the class, right? It doesn't belong to any individual object, right? So to call a static method, you use the name of the class to call the method and not an object reference. Good. Any questions about static features? Okay. Moving right along, so. Okay, so now we're back to fundamental object stuff, fundamentals of creating classes. Now I want to talk about this method called equals, which is probably the most important method in Java. One of the most important anyway. Okay, now, so you create some class like point2, right? You know that, well, you sort of know, I think, that every point2 object is actually a big O object, right? So in object-oriented terminology, we say that point2 inherits from the object class, right? Or is a child class of the object class, or something like that, right? You know that the object class has a bunch of methods in it that every other class gets, right? So if you make, whenever you make a class, you get a bunch of methods for free, right? One of them is toString. Another one of them is equals, right? Now, we've got a point2 class. We have not made an equals method for it yet, right? But if you call equals on a point2 object, it works, right? And that's because it gets the implementation of equals from the class object, right? So this works just fine. So if you have point2p, that's a new point, so it's the point11, right? If you ask, is p equal to p, right? The answer is yes, right? So it's true. Okay. So now I write p2 equals p, right? Now remember what this does, right? So when you write point p2 equals p, you make a new reference called p2, but you don't make a new point object, right? What you're saying here is that p2 is the same point as p, right? It refers to the same point object that p does, okay? So when you write p2 equals p, the answer is again true, which makes sense, right? Because p2 and p, they refer to the same object. Okay, now I use my copy constructor to make a point p3, right? Now p3 is a new point, right? Because there's a, well, you can see the new operator right there, right? So you know that there is a new point, right, whose coordinates is also 1, 2, right? And that's the same as point p. Right? So now you've got 2 point objects, they have the same coordinates. But if you write p3 equals p, the answer you get back is false, right? So as far as Java is concerned, right now, right, 2 points with the same coordinates are not equal. And that's probably not what you want, right? So this is what's going on in the memory diagram, right? So p, where's p? Here's p. So p refers to the object at address 600. So there's p, right? p2, well, that also refers to the address at object 600, right? So there's p2. p3 is a new point, and it refers to the object at address 700, so there's p3, right? Notice that their coordinates are the same, but they're different objects, right? Now remember, P and P2, as far as equals is concerned, are equal, right? So when you write P equals P2, you get true, but that's because they're the same object, right? When you write P3 equals P, you've got two different objects, right? So as far as equals is concerned, right now, the answer is false. They're not equal, right? So what you get from object, right? The object version of equals checks if two references refer to the same object. Right? So that's what it does. Right? It's the same as the is operator. Is it is? I think it's is in Python if you've used it. Right? So x equals y is true if and only if x and y are references to the same object. Now, do I tell you? OK. What that also means is that the following. So the object version of equals is identical to so if you write P1 equals P2, right, that's the same thing as the object version of equals. Okay? So when you use the equals equals operator with references, you're asking, are they the same object? Right? Be careful about doing that, because normally that's not what you want to do. Right? Especially don't do that with strings, because that's almost certainly not what you want to do. Right? So probably one of the most common mistakes that students make in this course, you have two strings, you want to check if they're equal, so they write is s equals to t. That's not what you want to do. You want to write s dot equals t. Right? The problem with strings is s equals t often gives you the right answer. But it gives you the right answer for a very weird reason. OK, now in point 2, right, I want 2 points to be equal if they have the same coordinates. Right? And so point 2 is what we call a value class. So it's a class that represents some kind of value. Right? In this case, it represents two-dimensional points. Right? So most value classes should support what's called logical equality. Okay? So logical equality, so that's the object version of equals is equality of identity. Right? Are two things the same object? Logical equality is do two objects have the same state? Right? In other words, do 2 points have the same x and y coordinates? Right? So that's what you normally want, or that would be the expected behavior of equals in a class like point 2. Right? So do 2 points have the same coordinates? Now, back when Java first came out, so in the mid-90s, there were all sorts of versions of equals flying around. Right? If you picked up any textbook back in the early days, you would find, so if you picked up any 2 textbooks, they probably told you to implement equals in 2 different ways. So there's a quote here from Angelica Langer. She's got this very nice page describing everything you want to know about equals, right? And the quote is, "One would expect that overriding equals, since it's a common task, should be a piece of cake. The reality is far from that. There is an amazing amount of disagreement in the Java community regarding the correct implementation of equals." Right? This is an old quote. So this issue has now been settled. And there's basically 2 different ways to implement equals. This slide is not the correct slide. I actually lost this lecture. So I had a lecture all made up during reading week. And then for some reason, it didn't actually save on my computer. So this is an old version. This is going to disappear in a couple of days when I update these slides. OK, so this is what we're doing today. On Wednesday, I'll show you a second way to do this. So for today, we want these 4 things to be true. Okay? So this is what's going to happen when we implement equals. An instance is equal to itself. Right? So x equals x is true. Right? An instance is never equal to null. So x equals null is always false. Today, we're going to say only 2.2 objects can be equal. Right? So I can't have a point 2 object be equal to something else, right? Like a string or something like that. That would be weird anyway. You wouldn't do that. Later on in the course, you'll see why 3 is important. For now, point 2 objects can be equal to one another. Okay? And then 4, instances with the same state are equal. So 2.2 objects with the same coordinates are equal. Right? So requirement number 1, an object is equal to itself, just means x equals x is always true, right? Which makes sense, right? An object should be equal to itself. And if it's not, so if x equals false, that's very weird, right? And that's actually not allowed if you look at the contract for equals in object. Okay? Now, remember, if you want to check if an object is equal to itself, you want to check if the you can use equals equals, right? So that's easy to do. So here's our method equals, right? So its signature is always public Boolean equals object object. Right? The parameter here, this is important. The parameter here is always object. And what that means is, in Java, you can ask if any two objects are equal. Right? So you can ask if a point2 object is equal to a string, or a point2 object is equal to a scanner, or is a point2 object equal to a list, or something like that. Right? Those are all legal to do. Okay? Remember, so we're using @override. Remember what @override does, right? So it asks the compiler to check if this signature is correct, right? Does an equals method exist in the object class with that signature? Right? Now, requirement number 1 says, are the two objects equal? Right? So I guess I should show this on the, I'll write this down too. Okay, now when I write p equals something else, or x equals y. Okay, so I'm going to do x dot equals y. Okay, whenever I write that, inside this method, x is this, right? And y is obj, okay? So if I want x equals x to be true, right, I can simply check, is this equal to obj, right? And then when you plug x and y in for this in obj, right, you'll see why that must be true, right? So if y is actually, so if you actually say x equals x, then you're saying, that's the same as saying this equals obj. Right? Now that statement doesn't actually need to be there, right? So if you leave this out, your method still works. The reason it's here is because it's cheap to check, right? All I have to do is check, are the two references the same? That's very fast to do, right? And if so, I can immediately stop and return true, right? If you leave it out, your method's still correct, okay? So requirement number 2, an instance is never equal to null, right? So the contract for equals says that x equals null must return false, right? So if you go and look at the object API, right? It will say right in, it's a big bold letters, it says x equals null, must never throw an exception, it must return false. Right? So that's easy to check for too. Right? So x equals null, so in this case, right, if you look up there, y is going to be null, right? Or obj is going to be null. Right? So if obj is null, return false. Right? Now remember what null means. Null means no object. Right? So you're asking, is a point equal to no object? So that should always be false. Now, unlike the first if statement, this one has to be here, right? At least for today. Tomorrow it won't be here, but for today it has to be here, right? Because in the next step, we're going to use obj for something, right? And if you use a null reference for anything, you end up with a null pointer exception. Okay? So this has to be here for now. Again, old slide, so this is going to change a little bit. So the implementation of equals that we're doing today says that only objects of the exact same type can be equal, right? Now this means I have to be able to figure out what is the type of y, right? Because if y is a string, I want to return false, right? Because only point2 objects can only be equal to other point2 objects. Right? So how do I find out what the type of an object is? Well, there's this method called getClass. Right? That's a method that's also an object. Right? If you look at the documentation for getClass, it tells you it returns the runtime class of an object. Right? So what getClass actually does is it returns an object of type class, big C class. Right? That object represents the class of whatever object it is that you called the method on. Right? So if P is a point2 object, right, then P.getClass returns some object that represents all point2 objects. Right? Now getClass promises for every class, there's only one object that represents the class. Okay? So for every class, there's exactly one object that represents the class. Right? So that means I can write the following line of code. Right? So if this getClass is not equal to Object.getClass. Right? So getClass returns an object that represents the class. In this case, it represents the point2 class. Right? Object.getClass returns some object that represents whatever class obj belongs to. Right? There's only one object of either class, so you're allowed to use equals equals or not equals in this case. Right? These are actually references. Right? That's a reference. That's a reference. Right? I just spent a whole bunch of time saying when you compare references, you probably want to use .equals, and now I'm using not equals. Right? The reason you can use not equals here is because getClass promises it always returns the same object for any class. Right? So there's only one object for each class anyway. Right? So you can actually use equality of identity here. Right? So all that's saying is if the two objects have different classes, return false. Right? That's all it says. Now, that's why the previous if statement was needed. Right? Because right there, I'm saying Object.getClass. Right? So I'm calling a method with the reference obj. If this if statement's not here, and obj is null, you get null.getClass, right? And you cannot call a method with a null reference, right? That immediately results in a null pointer exception in Java, right? Which is why that second if statement must be here. Okay, next step, right? So this is part 4. Objects with the same state should be equal, right? So the state of an object is just the value of its fields. Right? For the state of a point2 object is just its x coordinate and its y coordinate. Right? So I want to check, is the x coordinate of this point and the y coordinate of the other point the same? Sorry, are the x coordinates of both points the same and are the y coordinates of both points the same? But I have a problem. The signature for the method says that obj is an object. Right? So it says obj is an object. That means inside the method, right, whenever I use obj, I can only use obj to call methods that are in the object class. Right? If you get past this third if statement, so if I get to this line right here, right, I know that obj is a point2 object. Right? So I know that I know that I should be able to get its x coordinate and y coordinate. The compiler won't let you, because as far as the compiler is concerned, obj is an object. Right? So at this point here, I have to convince the compiler that obj is in fact a point2 reference. Right? So in other words, I have to cast obj now. Right? So right there, on the next line, right, I cast obj to a point2 reference. Right? And I store that value in some variable called other. Right? So on this line, I know that obj is for sure a point2 object, so I know that this cast will work. Right? And that's because if you got past this if statement, that if statement right here checks if the two objects have different classes. Right? So on that line there, the cast will succeed. Right? I have to do this because I want to get the x coordinate of obj. Right? And I want to get the y coordinate of obj. Okay, so how do I check now if all the fields are the same? Right? Do all the fields have the same value? So there's a recipe for doing this. Right? This is one of the reasons why there were so many different ways of implementing equals. Right? But if you follow the recipe, if you just blindly follow the recipe, everything works out fine. Okay? So if the field is a primitive type, right, and it's an integer or a Boolean, right? So it's primitive and it's integer or Boolean, you just compare the fields using equals equals. Okay? If it's a floating point type, don't use equals equals. Right? So if it's a floating point type, use the method float to int bits to convert the floating point value to a long value. Does that return a long? I don't remember if that returns to int. Sorry, no, that will convert the float to an integer value. Okay, so an int value. Right? If it's a double, you use the method called double to long bits, and that will return the long representation of the double number. Right? Now, the reason you're doing this is you can compare two integers using equals equals. Right? So if I call float to int bits, that takes the float number, converts it to an int, and now I can use equals equals on the result. Right? Double to long bits converts the double to a long, and then I can use equals equals to compare the result. Right? I'm just going to check something here. Okay, so on the next slide, I'll explain why you have to do this, or why you should do this. Okay, 4. If the field is an array, so if your class has an array and you want to check are the two arrays of the two, if you want to check if the arrays of the two different objects are equal, just use arrays.equals. Right? Don't write your own loop to compare all the elements of both arrays. Right? And if the field is a reference type, so for example, if your class has a list as one of its fields, right? Just use equals, the method, on the field. Right? You have to be aware that the fields might be null, but don't worry about that for this course, right? Because that shouldn't happen for anything that we do. So what does it look like? So that's what it ends up looking like. Right? So the recipe says I have to use step 3 because my x coordinate is a double and my y coordinate's a double. Right? So to compare the x coordinates of the 2 points, right, I write double to long bits this dot x, right? Convert the x coordinate of this point to some sort of long representation. Right? Convert the x coordinate of the other point to some sort of long representation. If they're different, then their x coordinates are different, so the answer is false. Right? Now you do the same thing with the y coordinate. Right? Convert the y coordinate of this point to some sort of long representation. Convert the y coordinate of the other point to some kind of long representation. If they're different, right, not equal, then the y coordinates are different, so you return false. Right? If neither of these if statements run, sorry, if the bodies if neither of the bodies of the if statements run, then you know that the x and y coordinates are the same, so now you can finally return true. Right? So again, the 4 parts. Part 1, right? X equals x should return true. Right? Part 2, x equals null should return false. Point 3, a point 2 should not be equal to a string object. Right? Point 4, are the fields, do they have the same values? Right? And if so, you can finally return true. Right? Okay, now why can't I just write this x equals other x? Right? And so the reason is inside the notebook that describes doubles, right? Or the floating point types. So the reason you can't write this x, or the reason you shouldn't write this x equals other x, is in case of this x or other x being equal to, is in case the 2 points have the same coordinates, but their coordinates happen to be nan, so not a number. Right? So if you have a coordinate, if you have a point whose x coordinate is not a number, and you have the same point whose x coordinate is also not a number, then nan, if you write nan not equals nan, you get true. So nan is equal to no other value, not even itself. Right? There's another weirdness with doubles. If you write, so if this x is equal to -0 and other x is equal to +0, then this x equals other x is true. However, if you do it this way, then -0 is not equal to +0. Right? So it's not equal to +0. Right? Which oddly enough is what you want if you want your objects to work with the other classes in the Java standard library. It's weird, but that's just the way it is. Okay? So those are the reasons. So those are very obscure, right? They almost never happen, right? Which is why if you just wrote this x equals other x or not equals other x, your method would almost always work, right? The problem is when it breaks, it becomes very hard to debug. Right? So if you just follow the recipe blindly without understanding why you're doing it, equals will always work. All right? If you want I think the explanation is in the notebooks. So if you've actually read the notebooks for equals, the explanation is in fact there. OK, so our version of equals compares the state of 2 points to determine equality. Right? So any 2 points that have the same coordinates are now equal, which means you can write code like this. Right? So here's my point P. It's -1, 1.5. Right? If I use the copy constructor to make a copy of the point, right? Then when I write P.equals Q, it's true. Right? So back on the first slide that I showed you, you would get false. Right? Now it's true. Right? So 2 points with the same coordinates are now equal. OK. There's something called the equals contract. So in the object class, if you read the documentation for equals, it's a very long piece of documentation, right? So the documentation spells out in great detail what equals must satisfy if you're to have a correct functioning version of equals. And it describes this in a mathematical way. So it says equals must be reflexive, symmetric, transitive, consistent, and it must not throw an exception when past null. Right? This looks scary, but it's not. Reflexive just means an object is equal to itself. Right? So x equals x is true, so that's not a big deal. Right? So where's symmetry? Here it is. Symmetry. Symmetry just means if you reverse the order of the operands, you get the same answer. So x equals y is the same as y equals true. X equals y is the same as y equals x. Right? So two objects must agree on whether they are equal. Right? X equals y is true if and only if y equals x is true. Right? So that's all symmetry means. Transitivity just means that is a relationship between three different objects. Right? So if the first object is equal to the second is equal to the third, then the first must be equal to the third. That's all that means. Right? So in other words, if x equals y is true and y equals z is true, then x equals z must also be true. Right? If you follow the recipe, if you follow the slides that I gave you before at the beginning of the lecture, all of this just falls out. You don't have to check it. Consistency. So this one's a bit of a weird one because you wouldn't expect equals to ever not be consistent. So if I have two objects x and y and I never change their state, right? So I never change their state, x equals y always returns the same answer. Right? In other words, the result of calling equals on two objects should be consistent. Right? It shouldn't be random. Right? So if the state of the two objects never changes, then the answer for x equals y is always true. Right? And you would think that, this should always happen, but it's pretty easy to create a class where this doesn't happen. Right? And finally, x equals null is always false. So that was requirement number 2, right, of our from earlier. And it should never throw an exception. Right? OK, so you need to make sure that all 5 of these things are satisfied when you create your equals method. Right? If you follow the steps that I've shown you in the slides, all 5 of these fall out. Well, sorry, 4 may not fall out automatically. But the 1, 2, 3, and 5 all you get for free, right? Just by following the steps. 4 is weird. It's hard to give you an example where you don't have a consistent equals. One way you can have an equals that's not consistent is if you're implementing equals, and then inside equals you change the state of the object for some reason. Right? So one of the things students like to do is they like to, if your object has a list in it, they like to sort the list. Right? And sorting the list might break the consistency requirement. OK, now what about, how about doing equals for some other type of object? Right? So what about the counter class? Right? Now remember the counter class has just got one field, that's the value of the counter. So equals should be very easy to implement, right? Step 1, right? Is the object equal to itself? Right? If so, return true. Step 2, is the parameter null, right? So x equals null should always return false. right? Step 3, check the types of both objects, right? If they're the same type, if they're different types, the answer must be false for today, right? Now, if you reach the next step, you know that obj and this are both counter objects. So cast obj to a counter object, right? Why do you need the cast? Because as far as the compiler is concerned, obj is an object, not a counter, right? So convince the compiler that obj is in fact a counter. And then the last step, test if the values of the two counters are the same, right? So this value equals other value is true if the values are the same, right? So you can simply return the result of that comparison, right? You don't need an if statement here, right? Another common thing you'll see here is if this value equals other value, return true, else return false, right? You can just return the result of the comparison. Okay, so on Wednesday, I'm going to show you a different way of implementing equals, and I'll explain why you sometimes need the second version. Okay, that's it for today. Reminder, your midterms are this week, right? And they are in your regularly scheduled lab time. So whatever lab you're signed up for, that's the time you're going to be writing it, right? So some of you are, in fact, writing it today at 3:30, right? And that's it. Thanks.